just want to go over some research I'm doing with the spin of the Earth. I got thinking I wanted to do up a diagram to show the different speeds that the atmosphere would be going. So what we're going to do is we're going to start off with this here is the equator slice. So basically we're looking straight down, top view on the globe model, cut it in half, so we sliced it right at the equator, and this is what we'd see looking straight down. So what I did is we're going to work with the diameter given. From there I just used pi and worked everything else out mathematically. So to keep this pretty basic and not to get different numbers from different sites that don't correspond with each other, so I'm just going to keep it simple. I took the one diameter from Wiki. It could be a little bit out from the actual. I know they're saying that at the equator it's wider than from pole to pole, but we'll generalize it so that we can figure this out. So I'm going to use the 12,742 kilometer diameter, and the spin of the Earth at that diameter would be on its surface 1,667 kilometers per hour. So half of that, if we're going from the edge to the halfway of it, and that's this dotted line in the center, we'd be looking over here, would be half that speed, because at the axis here, we'd be looking at 0. So that's at 833.5 kilometers per hour. Now I'll just show you quickly with the calculator how I went about just getting this base speed so you can see the math I'm using. So we're just going to take the diameter of the Earth, we times it by 3.14, which is pi. That gives us our circumference of the Earth, and then we just divide that by 24 hours, and that's how many kilometers it can travel over an hour. So there's 1667 point and then a whole bunch. So I'm just rounding it to the nearest solid there. So let's go forward here. Now I went and got the research, so the layers of the atmosphere go up, and we start with the troposphere. It tops out at around 17 kilometers. The stratosphere is next. It tops out at 50 kilometers. The mesosphere tops out at 80 kilometers. The ionosphere tops out at 640 kilometers. And the exosphere tops out at 1280 kilometers. Now, the highest man-made jumps are in the stratosphere. So just for reference, clouds sit at the top of the troposphere. Just for some references, these upper three layers get into the outer layers that go into space. So this outer exosphere would be considered the outer shell of the Earth, where the atmosphere reaches the highest, what they say. So now if we take the same calculation, because of course these are adding to the diameter, so we can then double that, so 17 would be 34, we add it to the diameter, and then we can just go and do the times by pi divided by 24 hours, and we're going to get our speeds. So it's not much more, like we go up 17 kilometers and we're looking at 1,672 kilometers per hour for the troposphere. And you can see here 1680, 1688. As it gets higher, it gets faster, of course, because as they tell us, the atmosphere keeps up to the spin of the Earth. And that's a little hard to believe, but that's why I'm doing this. So this next one here, what I did, you can see here this orange line. It's just referred to axis slice. So we go over to the axis slice, and this is cutting the planet straight down the middle from pole to the top, pole at the bottom. We've got our northern hemisphere this side, southern hemisphere this side. Now, when we're starting to look at this, I start to lay out how, because they always say that the momentum of the planet's always pushing out, so the gravity pulls us back in, so that keeps us vertical on where we are on the Earth. So let's lay this out. So now, first of all, we got to understand that the axis, though, goes straight through on this plane. So this axis is 0. It doesn't. It's at 0 kilometers an hour. It's where everything spins from, right? So that is our center point to this, to figure out some speed. So if we look at, see, this is the equator speed, and that was at 1667. So halfway from there to the axis at the North Pole, we should get roughly a speed of 833.5 kilometers an hour. Now, be mindful that that speed would actually occur if we drew a straight line through here. That speed should actually technically be back here. What I'm going to do is just forego the extra calculations to show the extra amount of speed it would require to be out here on a sphere, just for this demonstration, because we don't really need to be do that extra calculation to show that this doesn't really work out. So we got that speed, which should make sense. 0 halfway to its maximum would be its half, and likewise. And if you're standing here, like they said, everything above you should equal out to that ground. So in theory, that line should travel out in all these atmospheres, staying steady with that point on Earth. So if we divide every speed in half, these are the speeds we're getting. Now, this starts to pose a problem. Like here, we look at the halfway mark coming back, say for the speed to the outer shell going on a 45-degree angle away from the equator mark, and we're getting 416. Now, I'm going to bring up another picture here where I work some more. Now, if we take and dot that line across through the Earth, and you'll see here, what I did is I'm just going to use the upper exosphere. So half of that, 0 to its 1,000 here at its halfway marker from its 2002 down here, we get 500. You can see I marked it up. So 750 and 250 would be the halves of that. Pretty logical. I mean, and then we look at where the 416 is, and this is rough. I mean, this isn't exact, so I could, admit that this isn't to scale to the point where we can just refer off of our visual here that that's the intersection. But what I want to make clear here is that at this point, the speed is referenced for it to make its circular path this way, because remember, we're looking at the side views. So this axis is 0. It spins from left to right along this dotted line. Same with this point to this point, and then it returns to this point, this point. So you get my drift there. It's rotating around there. So that's the speed measured from here to there, not this blue line. It doesn't work like that. So the speed doesn't travel up to there, because this is always 0. So when we look at this further, we can see, let's put in some more marks here. Now I put this purple dotted line at the end to show, from the axis here to here, we calculated that at 2002 on the previous slice. That was the top view to show how fast this outer layer must be going to keep up to the surface layer. So if we dot that line out, because if this is 0, any distance from there to here, so if that's 2002, from here to here should be also 2002. So this dotted line represents the maximum speed. So from the axis, this line should be the 2002 kilometers per hour. So all the centrifugal force is going in one direction from this line to this one, and same this way and opposite. I'm just working on one side here, but you get the point there, that if the force is working this way, then these speeds, this 500 should stay steady right through. So if we're looking at this 416, can't be halfway in, it should be more up here, closer to our 500, which is, it's coming through my ground speed there at 833. Now, we start to see this, like if you start to look at these angles, no matter if this model is exact or close to being exact, it's exposing these angles of forces that aren't playing into reality. So if you're standing there and you got a force working down and one working up to make you feel like you're standing vertical, then how would the centrifugal force work when it's all pushing to the east or to the west, pulling you off. So it's going to make you want to slant towards the equator. But take a look at this. So what I did is I laid out this centrifugal force coming across, and that's the force of the spin working outward east to west, because it's not working north to west or north to south, because that's zero. So obviously the red lines represent our forces working outward from the axis of the planet's spin. And you can see here as we come down, it just happened to roughly line around Tropic Cancer and Capricorn, is the barrier of the speed of sound, where our speed, and this is quite remarkable, we can go from 0 all the way up to the speed of sound, break it, and for the equator and the area between the two, Tropic of Cancer and Tropic of Capricorn, is above the speed of sound, as I've graphed it out here. Now what I did was I took some dotted lines here to represent roughly how the gravity is working back towards the center of the planet, to keep everybody on as far as they're saying. Now when you're looking at this, logically this does not make sense. To me, I just cannot see how, at this line especially where the sound barrier is broken, how we don't see phenomenon of one sort or the other of the sound barrier, a physical thing being broken there. And it was quite interesting is that I actually investigated further about this, and I'm going to play some videos here. One is from Mythbusters. There's been an argument about how planes, how they aren't affected by the spin of the planet. So if they take off against the spin, they should never reach their destination if they're near the equator, because they're actually, the spin of the planet is faster than the plane traveling against it. Now, a lot of people have argued this, saying that it's relative to the ground speed and all this, but Mythbusters, this video I'm going to show you, is going to show you proof in favor of the fact that planes cannot fly and gain distance working against the speed of the planet. So watch this, and we'll talk.
Feeling that we are very close to a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector edition! Woo! We canceled out velocity!
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
You know, I love physics and I love science, but I don't like these theories and everything else they've come up with. So we really need to get together on this, and if someone's got Auto Cad, if they can help me out and redo my drawings, that'd be awesome. Thanks.
I would say that was fast.
So you guys still believe that the Earth is spinning faster than the speed of sound? Really? God bless.